So I think I've, part of the reason I write a course planner for my courses is to remind myself what my plan is, because I will forget. And so I think one of the things I forgot was that I had taken the time to, so like your next test is on chapter 4, basically. Well, I think the chapter 3 was what? Systems of equations, right? 2 equations, 2 unknowns, really. Chapter 4 is on polynomial multiplication, factoring, and then at the very end of it, equation solving, right? So we're still doing factoring at the moment. We'll finish pretty soon. But then after that, if you look at my course planner, I have chapter 7, right? So chapter 7 is on quadratic equations. So I'm actually going to go back. So actually, I told you that we wouldn't do complex numbers till the end of the course. That's incorrect. We'll be doing more complex numbers here in about a week. Okay? So I decided to just put all the polynomial material together because it's part of one coherent thought, rather than just like taking the quadratic equation section and just chucking it to the end of the course. I don't know, the book's organization to me is very illogical, really. But since you guys don't read the book, it's not a problem. So, so anyway, here we go, factoring. So I do think I owe you a handout on completing the square. I mean, I think I went through it pretty carefully in class. Hopefully you took notes and stuff. But I'm going to try to make you a handout that kind of walks through the process again. Yeah. Because it is something that I think it's healthy for you to know. All right? Now let's look at some examples to get started here. 3x squared minus 14x minus 5. That would be example 1. Example 2, we'll do 4t plus 10t squared, minus 6. Example 3, we'll try our luck against 3a squared minus a minus 4. Example 4, we will attempt to subdue 3x cubed minus 5x squared minus 2x. So there you go. These are the first 4 examples today. All right. So what's the annoying thing about all 4 of these examples? The what? Negative? They've got negatives? Yeah, that's true. They have leading coefficients which are not 1. That's right. So that's exactly the problem. So let's do this. 3x and x, and hopefully we'll not be driven. I mean, if we get stuck, we can resort to the completing the square technique, right? If we get stumped on any of these. But hopefully we won't, right? Hopefully we can use guess and check. So we put 3x there, we put x there, because that's how to get 3x squared, right? Now we look at 5. How do you get 5? You really only got 2. Well, it's minus 5, right? So either you got to have minus 1 and 5, or you got to have 1 and minus 5. Them's your choices, right?
So is the one of the 5, is that the one that's multiplied, or is 14? Like, do you have to multiply to get 5 or 14?
We have to multiply to get 5. So, like, generically, the pattern is this. If we've got, ax plus, let's say, b times cx plus d, and you multiply that out, right? That gives you acx squared plus, the way it goes is a times d plus b times c x, and then b times d for that last term. So that's like, when the leading coefficient's not 1, we don't just add the numbers. We have to multiply them by the leading coefficient, whatever's appearing next to the x. So it's a little bit more complicated. See, if a and c are both equal to 1, then this gets much easier, right? because then when we multiply this out, the pattern is, I don't know why I put these parentheses out here. Sometimes I have a problem with writing too many parentheses. You guys have a problem with never writing them. So somewhere in the middle is the right place to be. I say you guys, I'm stereotyping, I'm sorry. But, sometimes they're useful. So x squared plus b plus d. So that's how it works when the leading coefficient is 1. Life is so much simpler, right? You just multiply the coefficients to get the constant term, and you add them to get the coefficient of the linear term. But when there's numbers here, we had to think through it, But it's always the case that the constant term is just the product of the whatever we put here and here, right? So you got choices. May I suggest that we just make a choice? Well, we'll try one. I'll try the first one. -1 plus 5. Did that work? Ooh, it did not work, because 3 times 5 is 15. There's no way we're going to get back to -14, right? So I made the wrong choice. What do we do? If your first you not succeed, try again. In this case, just try again. And there you go. Factored. All right. Now, this next one, I'm going to suggest that we make one additional step before we try to do this one, which is to rewrite in standard form. So this is 10t squared plus 4t minus 6. I just think that's in our best interest. Now, annoyingly here, we've got there's a couple different things that could go on, right? We could do 2t and 5t, right? So we'll try that to start with, right? But what are the other choices that we, in principle, could make here? We could try 10t and t, right? We could try, I guess that's it. This is the other choice, if we're just using integers, right? Is there anything else I'm missing? I think that's it. The only way to write 10 is either 10 times 1 or 2 times 5, right? So those are the two. But I'm thinking the 2 and the 5 might be the case here. I could be wrong. All right, now what? 6. How do we get 6? Oh, there's -6. You could either do -1 times 6. You could do 1 times -6. We could do 2 times -3. We could do -2 times 3. Those are the ways that we can get 3. We can get -6. So which one of those? I mean, let's just try one, right, and see how it works out. -1 plus 6. Now, if that works, I would be very lucky. Let's see here. 10t squared. So, I mean, I've got the 10t squared, and I've got the -6, right? The question is the middle term. So this gives me -5t plus what? Plus 12. 12 minus 5 is 7. Didn't work. So let's try the 6 and the -1. Let's try 6 here, and 1 over here. See if that works. What's that do? What's that do for us? Well, that gives us a -30t plus 2. That's definitely not working. Let's try the 2 and the 3. So plus 2 minus 3. How's that go? Well, we've got plus 10. Hey, plus 10 minus 6. We got it. That's the one. But in principle, there's 8 different natural things to try here, because you can go through these 4 choices with this template, but you can also go through these 4 choices with the other template if the first template fails. All right? Okay, how about the next one? I guess I do, on your test, guys, when you find an answer, I like you to put a box around it, just for my grading pleasure. And so I should probably model for that for you in here. Answer. Woohoo. Okay, so here, looks like we're going to have a 3a and an a. And let's see here, we got -4. -4 you could either get from -1 times 4 or 1 times -4, right? Or what else? How about 2 times -2? This one's kind of funny because, well, I guess you could also, in principle, do -2 and 2, right? in the sense that I'm putting the first factor in the first one, I'm putting the second factor in the second one. There's an asymmetry there. So, I don't know, I'll just try. Does minus 1 and 4 work? I got what? I got minus a from the middle, and I've got what? 12a from the out. Oh, 12 minus 1 is 11. That is not what we have here, is it? So that one didn't work. Oh, how am I getting to 12? So it's always this times that, and that times that. That's how we get the middle term. So goes back to the FOIL. First, outer, inner, last. Okay, so next, I mean, you can do them in order, any order you like, but you guys, if you guys want to tell me the correct one, if you've already found it, you could. End my suffering. Did that work? Ooh, that did not work because, again, we've got that 12, minus 12 plus 1. It's minus 11 this time. That was no. We could have really, I mean, after we had that first time, we probably should have just skipped to like option 3 if we were going to be lazier, right? So let's try it. So we got plus 2, minus 2. Did that work? I don't know. That gives us 2a in the middle and minus 6a outside. Well, that didn't work because we got minus 4a, right? So we got to try. Man, I sure hope this other option works. Otherwise, we're going to have to complete the square. So now what do we got? We got 3a. We got minus 2a plus 6a. I got 4a. Huh. Curious. Minus 4.
Minus 4 in the first one, plus 1 in the second.
Did I not do that one already?
No.
Oh. Thank you. I have somehow missed a possibility, haven't I? So I shouldn't just be writing this. I should also be writing what? I'm missing 2 cases. Actually, oh, man, I'm missing. Oh, hideous. So I'm missing, by the way, 6 times minus 1 and minus 6 times 1. And I'm missing minus 3 times 2. We just got lucky that it worked in the first list last time. And 3 times minus 2. Those are other possibilities. I said there were 4 choices for each template. I was wrong. There are 8 in the previous example. Thank you, Sam. Very helpful. What's up? I counted them. 1, 2, 3, 4. It depends on how the number, the constant term factors. The more factors you got, the more choices you got. If it's prime, there's just like, and even up here, there was 4 choices, weren't there? See that? This I could have also written 5. What I failed to remember when I wrote these possibilities down to start with, is that it's not just the numbers; it's where they go. So because there's an asymmetry in these problems, you can go either way. So for a prime, in one of these kind of problems, there's 4 choices. For a composite, it looks like there's the number of factors times 4, I guess. Is that right? But it's not quite that simple. If it's a square, I don't know. Let's not. You don't want me to try to enumerate the combinatorics. That's not my game. But this worked, didn't it? So minus 4 plus 3 minus a. Very good. Thank you, guys. See, ordinarily when I teach this kind of class, what I will do is I will break you guys up into teams and have you work on boards for like 20 minutes in the class. But in the age of COVID, I'm not allowed. I'm not supposed to do that sort of thing, so I don't. But it is very healthy for you to try to work along as we're doing these examples, and I thank you for that. So how about this one? First move, we should do what? Factor an x out, right? So then we've got 3x squared minus 5x minus 2, right? First thing we do, factor the x out. Then I'll write a template. That's a 5, yeah. It's just a poorly written 5. Now, thankfully, we're dealing with the prime case here, right? So 2, we can either go minus 2, rather. So we can do minus 1 times 2. We can do 2 times minus 1. We can do 1 times minus 2. And we can also do minus 2 times 1. Them's your choices, right? So let's try the first one. Minus 1 and plus 2. What does that do for us? I get a minus x and a plus 6x. Ooh, but I wanted minus 5x, right? So that didn't quite work, did it? But if we just flip the signs, I think it will. What if we do plus here and minus there? Then is it going to work? I think it will. That gives me a plus x and a minus 6, which gets me back my minus 5x that I wanted up there. There you go. We factored it, right? So guys, the vast majority of questions that I ask on quizzes and tests tend to have leading coefficients of 1, because I can learn a lot about what you know by asking problems with leading coefficients of 1. To me, these kind of problems, these separate A students from B students, because these are significantly harder than the ones we were working for the most part last time, right? That leading coefficient not being 1 really makes it a lot harder, doesn't it? It really does. All right, that brings us to special factoring. And I don't mean, well, okay. Special factoring. So there are some patterns that we should be aware of. I've already showed you one of these sort of things when I showed you Pascal's triangle. So let me just, these are patterns of note. So I'll go with the easiest one to start with that we use a lot. A squared minus b squared is what? A plus b times a minus b, right? So that difference of squares formula, very, very important to know about, right? There's also the square formula. This is a good one to know about. So we sometimes, if we can see that pattern, that's lovely, right? We can use that to immediately factor something if we see that pattern. There's another one, though. Difference of cubes. A cubed minus b cubed. And this is a minus b times something. So here's how I remember it. To get the a cubed, I need an a squared. To get the b cubed, I need a plus b squared. And then I need to figure out what goes in the middle. I think it was plus ab. Now we can check me on that, right? So how do we check if this identity is true? How do we check? Just do what? Just oh, you say look it up in the textbook that you guys don't read? No? Google it? Oh, expand. I was looking for the word multiply, but you said expand. But expand is a completely legitimate alternative to multiply. Indeed, expand. So we have a times a plus a squared plus ab plus b squared minus b times a squared plus ab plus b squared, right? Did I remember it right? Let's find out. We got a cubed plus a squared b plus ab squared minus ba squared minus bab, also known as bab, and then minus b cubed. So what does bab cancel with? See, bab is actually the same as ab squared, right? Hey, this marker again. All right, this. Almost. Thank you. Oh, and then the other one, right? A squared b and ba squared, that's the same term, but with a minus. Those cancel. And we're left with what? A cubed minus b cubed. Right. So this is the difference of cubes formula. Sometimes this is useful. What if we had a cubed plus b cubed? How would that work? Yeah, let me instead say, instead of using b, let me just use a c here. And point out that that's the same as if we let c equal to minus b, right? Then this would be a cubed minus b cubed, right? Because c cubed, the minus is minus. What happens when you cube a minus? You get minus 1 times minus 1 times minus 1, which is minus 1 again, right? So the cube of a minus is just minus the cube. So if I make that substitution, I get back to the previous identity, which we already know. So I can write that out. Yeah. And then I can convert back to like b is equal to what? Well, minus b is equal to plus c, right? So I got a plus c and a squared. B is equal to minus c, right? So minus ac. And then b squared is c squared, so plus c squared, because the square eats the minus. So there you go. This is the formula for adding cubes. Now, I'm showing you tricks to derive these things if you know one of them from the other. But that's kind of a waste of your time in some sense, because you do get a formula sheet, and you can write these on the formula sheet, right? So you don't, I'm just reminding you, you should write these on your formula sheet. They might be useful, all right? You never know. So what's beyond this? Beyond this, remember I showed you last time, well, not last time, maybe it was last time. Was it last time? I can't remember. A plus b cubed. We worked it out. It was a cubed plus 3 a squared b plus 3 ab squared plus b cubed. Remember, I worked out the coefficients there from Pascal's triangle. And from that, we can do higher things like a plus b to the fourth and so forth, all right? I would say another important pattern to know about, and we had an example like this, but a to the fourth minus b to the fourth, if you have that, you can rewrite that as a squared minus b squared times a squared plus b squared. This pattern does appear in a certain collection of problems, right? Beyond all this, there's what's called factoring by grouping. Factoring by grouping is just another name for using the distributive property intelligently. Let me show you an example for each one of these, yeah? Because after all, we're factoring polynomials, right? This is just a alphabet soup, right? So, example 5. So if we had like, x squared minus 81, we go, wait a minute, that's x squared minus 9 squared, right? And so difference of squares says that that's x plus 9 times x minus 9. So that's how we would use difference of squares, right? Example 6, you might face something like x squared. Well, let me make it more exciting. You might face something like 4x squared plus 8x plus 4, right? So you could look at this as, well, that's 2x squared plus 2 times 2x plus 2 squared, right? And if you saw that pattern, you go, this is a plus b squared, right? This is 2x plus 2 squared. If I did that right? I think so. But this way I just did this problem, it's very complicated. Right? I think the way I just advertised to do this problem, it's not the right way. Can you tell me a better way to do this problem? What should we do when we face a problem like this? Like example 6. What should we do? I don't think we should do it the way I just did it. I don't think it's a good way. There's a better way. What's the better way? Anybody? What should I do? What's that? Use 2 and 4. Something about 4 is the right idea. Yeah. Do what? There's a 4 in everything here, isn't there? So what could we do? We could factor out 4, right? If we factor out 4, life becomes easier because this is 4 times x squared plus 2x plus 1, right? And then it's much easier to use this square formula because we can readily see that that's x plus 1 squared from the pattern. Which is, by the way, a better answer, right? You could have got that from the one above if you factored the 2 out and then used properties of squares. Right? So like the problem above could be simplified to that. But if we just factor the 4 out to start with, then life is, that's a better way to be, right? All right. The difference of cubes formula is pretty impressive, really. If we have x squared minus 8, right, that's x cubed minus 2 cubed, right? And so how does that factor? It factors easily with the difference of cubes formula. It factors not so easily without it. I mean, I don't know. X squared. Here a is equal to x. B is equal to 2 in the cube formula over here, right? So I have x minus 2. A squared, AB is plus 2x, right? And then b squared is what? It's 4. Question, can I factor that? Is that completely factored in this case? How could we decide? We could look at the discriminant, right? If the discriminant is what? Negative, it cannot be factored. What's the discriminant here? I'm talking about the discriminant of this piece. So a equals 1, b equals 2, c equals 4. Discriminant, b squared minus 4ac is 4 minus 4 times 1 times 4, also known as minus 16 plus 4 minus 12 less than 0, cannot be factored, right? Cannot be factored. This is an irreducible quadratic factor. So we're done, by the way, if we were asked to completely factor this polynomial. It turns out anytime you have a difference of cubes, the quadratic which appears is irreducible. This is like not a one-off. This is always the pattern. So I think that's good. I'm going to stop here in terms of examples. We could do more, but I want to shift over to factoring by grouping. You should see a few of those. That is an important technique we should talk about. So let me see if I can find in your book the examples. Oh, come on. I thought I had it. It just tells me to factor. Well, that's annoying. I'm going to have to, oh man, I've been driven to look at the index. Factoring by grouping. I thought I just had this section open, but now I can't find the problems. Grouping method, 319. Okay. Never mind. It doesn't have examples. So this must be one of those cases where I'm remembering pre-calculus. My apologies. You know what I mean? So I'll go back to your homework printout. Here's an example we haven't worked yet. So let's try this one. Where am I? Example 8. See if you guys can do this one. Minus 5a to the 4th plus 10a minus 20. So here we're just asked to factor out a negative coefficient. Whoa. It asks me to factor this completely. That doesn't seem right. Am I missing something here? I don't know. Let's try it out. So factor out the minus 5. What we got? It doesn't seem like that's a reasonable question for you guys as I look at it. Maybe I'm not seeing something here. Plus 2a, right? Minus what? Plus or minus 4? Minus 4? Oh, okay, plus 4, yeah. Because we want the minus 20 back, right? I think there may be a typo in your homework, honestly, like number 10 in section 4.3. This problem becomes reasonable, I believe, if you, instead of having a there, have a squared. If that's a squared, it becomes a reasonable problem. With a, that's a nasty problem. With a squared, we could do it, all right? So I'm going to add an a squared. I'm going to make it squared, because if we do that, then what we can do is make a substitution, all right? So let's substitute. I can't spell substitute. Substitute. Hey, wait a minute, what am I doing? Substitute. There we go. X equals to a squared. If x is equal to a squared, then x squared is equal to what? A to the squared squared, also known as a to the power 4, right? So if we convert this to x, we're doing a lot better, right? This is x squared plus 2x plus 4. Oh. Ooh. It's still bad, guys. Oh. Oh, man. All right, fine. I'm just going to do it, and then we'll erase this from the record. See, when I complete the square there, I get x plus 1 squared. And then I subtract 1, but subtract 1, add it to 4 gives me 3. So this quadratic cannot be factored over the reals, right? Which means that I do what? I can factor it over the, oh man. Oh, So 3 is I times the square root of 3 times minus squared. Well, it's minus I times the square root of 3 squared. So I do plus I root 3 x plus 1 minus I root 3. Oh, no. No. Strike this from, you may scribble through this one. No, I am not doing this in here. That's wrong. So, I believe problem, man, unless I'm just not seeing something, I think problem 10 in section 4.3, you can skip that one. 'Cause I don't think it's something you can do. In the homework. I mean, factor out the minus 5. Sure, we can do that. That's fine. But it says factor completely. That I don't think is a reasonable question. All right, because it was a quartic that I had written, which means it can be factored either into a product of two irreducible quadratics or into a product of like a linear times a cubic, a linear times an irreducible quadratic. Like it can be factored. There's a theorem of algebra that it can. But the fact that it can doesn't mean that the algebra to do it is a reasonable question for an intermediate algebra class, right? Like it may involve square roots of square roots. It's just ugly. So sorry. That's what I get for using your homework. That's your example. So that example didn't count. This is example 8. Here we go. Minus 4r squared plus 16r. Can we factor this one? Well, there's number. I finally found a factoring by grouping problem in your homework. Here it is. So this is what? I can factor out what? How about minus 4? Then I've got what? R squared. How do I get 16? Minus 4 times minus 4, right? Minus 4r. What can I do next? Well, I've got an r in both places, right? So I can factor r out. Minus 4r, r minus 4, r. It's done. So. I do want to teach you factoring by grouping, but I'm frustrated by the lack of examples in your book to give you. I mean, there's just this one. This is problem 17 from section 4.3. X cubed plus 3x squared minus 6x minus 18. We're supposed to use quote-unquote factoring by grouping. Let me give you an example 10. Suppose you've got x to the 4th plus x squared plus 3x squared plus 3. I'll do this example first, and we'll come back to the other one. See, what I could do here is I could go, wait a minute, I've got x squared times x squared plus 1, right? That gives me these two terms. And what's the second two terms go to? Well, that's 3 times x squared plus 1, right? So then we can do what? We can use the distributive property to regroup these, right? Because this is the same as what? See, this is the same as x squared plus 3 times x squared plus 1, right? And that's it. That's completely factored because both of the factors there are what? They're irreducible, like we talked about last time, right? So there you go. So how about the one above? Like this is the one from your homework. You probably literally have this homework problem in your homework, I think. I think it's randomized. So how would you, what do you, how about the last two terms? Can we see something there? So these two, what's that? That's minus 6 times what? X minus or plus 3, right? Is there an x plus 3 to factor out here? Oh, there is, isn't there? So we could go x squared times x plus 3, couldn't we? From the first two terms, yeah? And then what do you got? Well, you got x squared minus 6 times x plus 3. Both of these examples illustrate what's called factoring by grouping, which I think that the name of it kind of makes sense, right? See how that factoring by grouping, that's a good name for what we're doing. You're grouping stuff so you can see how to unmultiply it. Or, yeah. See how you're grouping some things so you can see how to recognize it as a product of things. Now, we're not done there. Can we simplify that further? Well, I just told you we're not done, so yeah, you can simplify it further. How can you simplify it further? Hint. 6 is equal to the square root of 6 squared. So x squared minus 6 is the difference of squares. Right? We just have to see it that way. So x squared minus 6, we can factor as x minus the square root of 6 times x plus the square root of 6 times x plus 3. And that would be the answer here if you were asked to factor it completely. All right. So I think at this point we're around about 40 examples of factoring. So I'm gonna go on. You need to do your homework. Like, you cannot learn this from watching somebody else do it. I think I've showed you like every pretty much strategy that I know and use. So try it out for yourself and see how it goes. Excuse me. Section towards the end of this chapter, 4.8, we start facing questions with polynomial equations, all right? So we need to talk about that. What's a polynomial equation? Uh-oh. Did I ever move the camera? Oh, me. Well, we got that part. Sorry, folks who are not here. I've been over on these two boards for, I don't know since when. And I don't think I've ever erased anything here since I moved the camera, but anyway. You're like, that's why we come to class. Also for the excellent jokes. You guys are mean. That was sarcastic. I feel like you need to say that. All right, so what is a polynomial equation? And how do we solve them? So a polynomial equation is basically something of the form an x to the n plus a2x squared plus a0x plus a1x, oh, excuse me, my bad, a1x and then a0. What's wrong with me? Good grief. Equal to 0. So a polynomial equation has the generic form like you set a polynomial equal to 0, and then you ask which x will solve it. All right? So let me give you a quick rundown of the theory. What's the theory say? Theory says there exists n complex solutions. Oh, I'm sorry. I've just used a hieroglyphic symbol on the board. Let me fix that. Theory says there exist n complex solutions to the above equation. So here I'm assuming an is not equal to 0, all right? Now, if the coefficients are real, the complex solutions have to come in what are called conjugate pairs. We'll talk more about that as we go on. And they can also be real, right? But the key thing I want you to take away from this is if you have an nth order polynomial equation, you can have at most n solutions, all right? And the reason for this, among other things, is we have a theorem which says that, let's call this thing P of x, all right? Which says that P of x, well, let's see here this way. P of c equals to 0 is equivalent to P of x having a x minus c factor, all right? I need to use something else here. I'll say Q of x. This is the some other polynomial. So this is what's known as the factor theorem. The factor theorem says that if you have a number which solves your polynomial equation, then there corresponds a factor in the polynomial equation. So think about it. If you had like more than n solutions, you'd have more than n x minus c kind of factors. And if you multiplied those out, then you'd have a polynomial which has a larger degree than n, which would be, you know, inconceivable. So that's the main two theoretical results to know about, all right? Now, how do we solve it, though? This is where factoring comes into play. So there's a principle. So this is just, you know, real numbers. If we have a times b equals to 0, what does that say about a and b? If a and b are real numbers and you have a product of a times b is equal to 0, this means that either a is 0 or b is 0, or they both could be 0, right? But them's your choices. So in mathematical terminology, a equals to 0 or b equals to 0. Mathematical or allows them both to be 0, all right? Now, so example, well, this is example 1 for polynomial solutions. So I guess it's example 11. I always example by the day, so it's example 11. So if we had x squared plus 3x plus 2 equals to 0, and we wanted to solve that, right? We want to solve that equation. First of all, how many solutions do we think we're going to get? At most 2. At most 2 real solutions. So we factor this. This is x plus 1 times x plus 2. Right? That's how you factor that. So we have a product of 2 real quantities, which is 0. The only way that can happen is if what? So this says that x plus 1 equals to 0 or x plus 2 equals to 0, right? Which says what? These equations you can solve for sure, right? X equals to minus 1 or x equals to minus 2. There you go. Them's the solutions right there. So this is why we've been factoring, because when you factor the polynomial, you can solve polynomial equations. Piece of cake. Knowing the factorization is almost the same as knowing the solutions to the equation to which it corresponds. But you notice we have not been working with equations up to this point. We've been working with expressions. What's the difference between an expression and an equation? An equation involves setting an expression equal to another expression, and then you're looking for values that you can put into the variable which make it work, right? An expression on itself is just an expression. It's like a word. These things over here were expressions. See, if I asked you what was r, or what was x, or what was x here, those would not have been reasonable questions. The answer is, it's a variable. It could have been a lot of things, right? But when we have an equation, it turns out different kinds of equations have different numbers of solutions, right? there are some equations with no solutions. For example, this one. What if we were going to solve x squared plus 1 equal to 0? Find real solutions to this equation. Well, what is this equation equivalent to? This equation is the same as x squared equal to minus 1. Well, noted. So if x, is this possible? Is it possible to have a real number squared, x, equal to a negative? Think about it. That's impossible, right? So there is no real solution. But is there a solution? Right? Is no real solution. But, side comment, however, by the way, x squared plus 1, remember, is x squared minus I squared, which is x plus I times x minus I, right? And if you set that equal to 0, that gives you x plus I equals to 0, or x minus I equals to 0, which either gives us x equals minus I or x equals to I. So, as I was saying, the general theory says there are always n complex solutions. Indeed, this second order problem has two complex solutions, plus I and minus I. That's called a conjugate pair. When you switch the I to minus I, that's conjugation. But if we're looking for just real solutions, what I just wrote in blue doesn't matter, right? That's not the solution we're looking for. So instructions matter. On the next test, if I say find real solutions, and I give you this problem, it's easy to say, there are no real solutions, right? But if I say find all the solutions possibly complex, then you would need to go through this, right? We're going to talk more about this as we go on, okay? So we're not done with this discussion. We'll come back to it as we cover chapter 7, okay? So let's look at another example. Another one. Example 13. What if we had x minus 2 times x plus 3 times x minus 10 equals to 0? So I already did the factoring for us to make it easier. All right? What are the solutions? So if we had x minus 2 equals to 0, that would be a solution, right? If we had x plus 3 equals to 0, that would be a solution, because it would give us 0 times other stuff, which gives us 0, right? And the third possibility is we could have x minus 10. The x minus 10 equals to 0. That would be a solution, right? So what does that give us? X equals to 2, x equals to minus 3, and x equals to 10. So this is a third order problem. It has, as it happens in this example, 3 real solutions. This is not surprising. We can't have more than 3. Right? Now we don't have to have 3. We don't have to have 3. Here's example 14. We could have something like x minus 1 times x squared plus x minus 1, right? We could use our newfound friend factoring by grouping to rewrite that as what? I'll give you guys a second. See if you can figure it out for yourself. Factoring by grouping. What should we factor out? Might not move the camera again. Golly. No, I got it. It's weird. I need glasses. Oh, they're in my office. How about x minus 1, perhaps, right? See, because we have x minus 1 times x squared, right? This gives me these first two terms, right? And then this, I just put plus 1, right? So this cubic equation, right? Do you see that it's cubic? Maybe you don't see that. Let me multiply this out just to show you if you didn't see it already. If I distribute this, I get x cubed minus x squared plus x minus 1, right? This is a cubic polynomial. It is degree 3. Now, if we set that equal to 0, right, what are the solutions? Well, we either have x minus 1 equal to 0, or we have x squared plus 1 equals to 0, right? Now, x minus 1 equal to 0, that one's fine. X equals to 1. Hooray. And if we have x squared plus 1 equal to 0, well, as we just discussed in example 12, no real solutions, right? So this is a third order equation which just has one real solution. Any questions? Let me just stop and point out something. Do you see the pattern here, what's going on? When we factor something, we get what? We get x minus c. See that? We get x minus c in the factoring, right? But the solution is c. Do you see that pattern? We have x minus 2. That means that the polynomial equation has solution 2. We have x plus 3, but that means that the polynomial equation has solution minus 3. We have x minus 10 as a factor. We have x equals to 10 as a solution. There's always this interplay of minus and plus between the factor and the solution, right? Be aware of that. It's something that students a lot of times like slips past them and they make errors on this, you know. But there's no need because it's really simple, right? Example 15. What if I had x squared minus 25 times x squared minus 100 equal to 0? How would I solve this? The answer to any question that I ask you how to solve this, it's pretty much going to be factor it, all right? Factor it completely. These are both differences of squares, so we can factor how? 25 is what? It's 5 squared, right? 100 is 10 squared, right? So we're really looking at x squared minus 5 squared times x squared minus 10 squared. So that factors to x plus 5 times x minus 5 times x plus 10 times x minus 10. Right? So we've had the talk, right? The solution is opposite the sign of what appears in the factor. So now that we've had that talk, I set this equal to 0, and I tell you this means that x equals to minus 5 or 5 or minus 10 or 10, solve the equation. We don't really need to write, right? Writing this is optional. All right? I've written it for you in the first few examples we've done because I'm trying to emphasize the internal logic, right? It's that the product of things being zeros means that there has to be a factor within that that's 0, right? But after the dust settles, we don't want to write all that. So we can just write down solutions once we have the factoring, right?